new sodium-ion batteries, which means that, unlike the lithium, you need to find new electrodes and new electrolytes. So this research has been booming over the last year. This is more or less what happened here in 30 years, where a few materials have been found, and you can see what I will say the battery workforce is coming into the scene. You can see that in 7 years, the amount of compound that has been designed and has been tested for batteries and so on. And among them, I will say, we found the same type of family that we had initially for the lithium ion. And few technology has been developing, as clearly indicated there, and what I will briefly focus here on this type of polymeric compounds. And here again, showing you how a ping-pong game between fundamental and applied research can lead you to some development. So what we are looking at is this type of system where you have, in this case, this NVPF, which is sodium 2,3V2PO4 2 times F3 and carbon. And when you look at the voltage composition curve, you have this cell voltage as function of capacity, which output voltage of 3.6 volts. If you look here, you have huge irreversibility, which is due to the consumption of sodium by this SEI layer. So in order to bypass this issue, we need to design new materials in order to bring enough sodium into our system. And what we have found, and we have done, we use, in this case, this new phase that we prepare by sample ball milling at room temperature using the precursor phase NVPF and sodium metals. And in this phase, we have been able to develop and to assemble some 18650, and these were the first type of cell assembled worldwide about 4 or 5 years ago, where at the first, we were very impressed by the performance at room temperature, since a few prototypes were displaying about 4,000 cycles, and with here a huge power rate performances that it was quite far better than in the case of lithium ion. So it was a good news, but it didn't last too long, because we have some bad news that when we want, of course, to use these batteries at high temperature, when I mean high temperature, it's not too high, 55 degrees C, you can see that now we have a drastic capacity decay and huge cell discharge. So which means in this case, we need to go back to fundamentals, try to understand why it was happening, and this was due to one component of electrolyte, which was a linear carbonate DMC, and we need to replace it. So we have done a large amount of theoretical and experimental work, and we come out with, in this case, this electrolyte, ECPC, with these magic cocktails that I will call, because we have 4 types of additives that are here together, and it's by their synergy, they can really improve the performance. And indeed, we could improve the performance. This is, in this case, what we could reach at 35 degrees C, where you can see now nicely the superimposition of voltage composition curve and the nice capacity retentions. And this has led to the creation of the development of a company, Tiamat, for commercializing this kind of sodium-ion cells. But when you look at this, you have a good cycling performance, excellent power rate capability, but still nothing is perfect, because we have a limit energy density. I mentioned about 110 watt-hour per kilogram compared to about 220 in the case of lithium ion. And of course, I mentioned about sustainability, we still have vanadium. So, which material alternative? And here again, we need to go back to chemical design, we need to go back to inorganic chemistry, which is essential in this issue, and we need to design new phases. I will make the story short. Over the last 1 or 2 years, we succeed in finding new layer compounds, in which here you have layer materials, which is a complicated formula, where we have done a double substitution of the manganese and the nickel in order to modify the ionicity of the crystal lattice and to increase the potential so that this material will be more water stable. And just very recently, we also succeed in making a new phase, a new O3 type layer compounds, where in this case, we also take advantage of the ionic redox process. So all these materials have been benched, again, NVPF, and you can see that now we can have really, in this case, capacity or energy density greater than NVPF. So we are close here, and I think now this is more or less where we are in our development. This is the first generation of batteries that have been based on NVPF, and we are developing now the second generation based on this new layer oxide. And what are the added value of this technology? Lower cost, high power rate, zero voltage storage, and the market targets are for fast batteries, which can be used in part of electric vehicles for replacing the Skype batteries or for grid sustainability. And I think this is great, but we should be modest. Because you see here, there is a French writer, a visionary writer, Jules Verne, that 150 years ago exactly has predicted already that the sodium-ion technology will be the best for sustainability and certainly the most interesting in terms of energetics. So as you can see, we can do great research to finally go back and find out what people have really foreseen 150 years ago. So this more or less will conclude the second part of this presentation. And now I would like to bring to my third part, that is the most exciting, where the field is going and what we are doing nowadays. So how to develop smarter batteries, which means that we are going now to try to add some sensing, some monitoring, and some self-healing functionalities. So why we are doing this and how does it happen? We do this for a simple reason that the latest evolution into our field of batteries doesn't come from science, they come from a businessman. And this businessman is Elon Musk, which are heavily revolutionize the field. Revolutionize the field by daily his obsession about the cost. So what is planned is that the cost of a kilowatt-hour of lithium battery will be daily less than $100 by 2024. And this has been confirmed by other companies, are clearly indicated here. How this stuff is going to be done, more or less, the equation is relatively simple. Chemistry material performance is using the same type of chemistry, which is NCA or NCM. Volume production, of course, is bulk gigafactory, but the key issue is battery second life. What does it mean? Is now you want to give two functionality to the batteries. And if you want to do this, you are obliged daily to have battery traceability. So this is more or less what I would like to talk about it and what happened. And in this case, we are going to get inspiration from the field of medicine, which means we want to add smartness to the battery. And you can see, for instance, in medicine, you can introduce sheep and human, and you can really treat some diabetic patients. During an operation, you can put optical fiber, and you can transmit information from inside of the battery to outside the batteries. So our view is that in 20 years from now, certainly, the battery will not have any longer a positive and a negative output, but you will have also an analytical output. So to do so, you need to build in some functionality, which means we are going to put sensors, optical, electrical, and so on. And of course, these sensors have to be transparent to the chemistry of your system, as well as to the manufacturing of your system. So how we do this, and let me show you an example of what we are doing presently, where, for instance, we are really putting an optical fiber into our 1850 cells. And what you are looking here is the voltage as function of time, and you can see in temperature, and you can see this kind of spike here, which are very interesting. The first one is really the energy associated to the formation of SCI. So which means that we have here a mean to control the SCI formation. Then the second spike here is associated to the phase transition for NVPF and so on. So which means that by doing this, we can do in-life microcalorimetry of our cell. Now, we can play with these optical fibers, and you can now, this kind of microstructure optical fiber, where now, as clearly indicated in blue, we can also control the pressure during the process. So this, great, but now, if we can identify cell failure like tumors in humans, question is we can develop self-healing processes. And this is more or less what we are looking now, how we can introduce in our system some self-healing process to do some vectorization and so on. And we need to design chemical functionality for self-healing process. So where we do this, we are using our battery separator, in which we are going really to put all these toolings. And what we are doing, as a matter of fact, is an example that was given by Jean-Pierre Sauvage during the presentation, where now we are going to create, by supramolecular chemistry, all this kind of really flexible polymer, where in this case you see a thread PO, in which we put cyclodextrin to do some repairing. And to do so, we can get this kind of self-healing polymer. And our vision, final vision, is here, where we believe that in 20 years from now, the battery will have the sensing. If there is a deficiency in the battery, we send it to a BMS, will activate a self-healing process, and so on. So this is more or less the view that we are developing now, as a matter of fact, at the European level, and the battery 2030 project. So, time to conclude. So what I try to show you today here, the science and innovation going to the field of batteries. Of course, bottom line, playground is the Mendelleev periodic tables. And I think as a chemist, we are not too bad to structure, to design new material and so on. We can make 100 materials, but maybe only a single one will be really good for battery application. So we need to go faster. And I think nowadays, we are going to have to use computational chemistry, artificial intelligence, to establish a material genome as it has been established before. But be careful, in genomics, people play with 4 elements. The periodic table for us is about 110, so it's quite more complicated. Then I show you also how microscopy was very useful to go down at the local level, look at the local structure and so on. What are the dreams? I think the dream in the future is we'll be able to really detect the electron. If we could detect the electron, we'll have really all the clues of all the redox processes that are governing photovoltaics and batteries, electrocatalysis, and so on. I think we heard at the beginning of this conference a presentation of detecting single molecules, why we could one day don't detect single electron. And of course, you have also trying about health for batteries and so on. So, final conclusion, and I think very strong, I think I tried to show you that the field take advantage of the synergy between scientific and technological knowledge, and this is essential for battery research. And I want to repeat, basic research must prevail. And this is not me who's telling this stuff, is one of the French famous oceanographer, Jacques-Yves Cousteau, write, applied research generates improvement, not breakthrough. Great scientific advance spring from basic research. And with this, I would like, of course, to thank all my colleagues at the Collège de France who have been working on different aspects of this research, and I want to thank you all for your attention.